Since the first time humans looked up at the night sky, the moon has always been a legendary symbol, a gentle light amid the endless darkness. It is a mysterious companion, a dream to aspire to, and the story of explorers endlessly yearning to conquer. The first footsteps on the moon's surface were not just a victory of technology and human will, it was a great leap forward, opening the door to a vast universe, challenging all limits, but behind that glory lie countless untold stories, challenges, sacrifices, and secrets never before revealed. Now, dim the lights, relax, and let yourself drift into space. Let the magical stories of the moon take you on an inspiring journey of discovery tonight. If you love exploring history and humanity's wondrous tales, don't forget to hit like and subscribe to the channel to continue this journey with me. Now, let's begin. Heading to the moon, where humanity's greatest dreams first took flight. Earth is an incredibly fortunate place, possessing all the necessary conditions to create an environment where life can exist and thrive, while also being protected from the many potential threats that lurk in outer space. However, once humans step beyond the boundary of our atmosphere, what greets us is nothing but coldness and death. This vast expanse of space is a place where there is no oxygen, meaning we cannot breathe out there. Furthermore, sound cannot travel in this environment, so if you run into trouble, no one can hear you call for help. If you scream for assistance, the only response you'll receive is absolute silence. Space is deadly like that. Yet, since the 1960s, humans have continuously sought ways to reach this lifeless realm. Why is that? Why are we so determined to go to a place where life cannot exist? What drives us to make such great sacrifices? Welcome to Season 6 of Stories from Outer Space. Now, let's explore the journey to the moon. As society continues to develop, humans increasingly strive to resolve conflicts through the most peaceful means possible. This helps minimize unnecessary confrontations. However, disagreement isn't necessarily a bad thing. If Vietnam hadn't launched its revolution for national liberation, would we be independent today? If Lincoln hadn't supported African Americans, would slavery still exist now? What about the Cold War? In 1945, the Allies were close to defeating the Axis powers. During this period, Allied leaders held two major conferences to decide what should happen after the defeat of the fascists. However, things didn't go as expected. The two meetings gradually turned into confrontations, igniting a prolonged conflict that would follow. The Cold War began with the Yalta Conference, attended by the three key Allied leaders: Winston Churchill, Franklin Roosevelt, and Joseph Stalin. The main topic was the post-war division of territory in Europe. Unfortunately, the conference failed to reach a consensus. The disagreement was understandable. Each of them had their own goals. The United States, a nation isolated on the other side of the globe, held tremendous military power. The United Kingdom, where the sun never sets on its horizon, and the Soviet Union, the world's largest territorial power. As giants on the world stage, none of them could allow another to become stronger or threaten their position. Therefore, post-war territorial division became an unsolvable issue. Because of unresolved differences, the Allies organized another extended meeting at Potsdam, Germany, from July 17 to August 2, 1945. Unfortunately, Franklin Roosevelt had passed away by then, so his successor, President Harry Truman, attended the conference. With the balance of world power on the verge of upheaval, the meeting took place under extreme tension. Having been left out by the UK and the US during the fight against Nazi Germany, Stalin became suspicious of hidden agendas behind the Allies' actions. Tensions peaked when Truman revealed the secret Manhattan Project. After the meeting ended, the relationship between the US and the Soviet Union officially fell apart. Just days after the Potsdam Conference, the US dropped 2 atomic bombs on Japan, bringing World War II to a final close. Witnessing the destructive power of such weapons, Stalin realized it was time to fight fire with fire. Oppenheimer and his colleagues had secretly created a mushroom cloud. So Stalin would secretly build his own strength. From that moment, the Cold War officially began. After subjecting Japan to 2 atomic bombs, President Truman declared to the world that the United States possessed the greatest military power by holding the capability to produce nuclear weapons. This announcement signified that American technology had surpassed the rest of the world by decades. To balance power with the United States, the arms race commenced. During this period, the Soviet Union was rapidly executing projects to develop nuclear bombs to catch up with American technology. Just 4 years after the Potsdam Conference, on August 29, 1949, the Soviet Union successfully tested its first nuclear bomb under the project named First Lightning. It seemed that the balance of power had been restored. However, during those 4 years, the United States continued to develop and created a bomb with a destructive power many times greater than the nuclear bombs previously dropped on Japan. It was so powerful that it produced a fireball covering an area of up to 65 square kilometers and obliterated the Marshall Islands from the world map. Following this series of events, the race between the Soviet Union and the United States became more intense than ever. In the subsequent years, the Soviet Union continuously achieved successes in its competition with the United States and began to expand its influence globally. The Soviet Union also initiated the first military actions during the Cold War period. By establishing relations with North Korea, the Soviet Union once again threatened the borders of the United States. Recognizing this expansion, the US government and NATO increased their power by incorporating and supplying weapons to West Germany. In response, the Soviet Union established the Warsaw Pact to build a defense line among countries including the Soviet Union, Albania, Finland, Romania, Hungary, East Germany, the Czech Republic, Bulgaria, and others. The pact was commanded by Soviet General Ivan Konev. The formation of these 2 military blocs officially established a bipolar world order and marked the global spread of the Cold War. Throughout the Cold War, the relationship between the US and Soviet military blocs remained in a state of high alert. Elite forces and modern weapons were mobilized at full capacity to counter any surprise attacks. At this time, with ballistic missile technology inherited from the Germans, the Soviet Union could attack the United States within just 30 minutes. This capability caused the United States to live in fear for an extended period. In the following years, the United States increased its number of nuclear warheads from 1,000 to 18,000. However, the Soviets proved to be more strategic by elevating the battleground to a new level: space. With their advanced rocket technology, in 1957 the Soviet Union launched Sputnik 1, the first artificial satellite into Earth's orbit, marking humanity's initial venture into space exploration. This was an achievement that the United States had not yet dared to dream of. During World War II, Wernher von Braun, an Axis engineer, developed the V-2 rocket, a terror on all fronts for the Allies. This technology instilled fear in both the Soviet Union and the United States, especially after the war ended, as it could fall into anyone's hands. After defeating Nazi Germany, both American and Soviet intelligence agencies aggressively sought the V-2 rocket technology and its creators. The United States emerged victorious in this pursuit. Following Germany's defeat, the United States secretly brought von Braun and many other scientists into its military to redevelop the V-2 rocket project into medium-range missiles like Redstone and Jupiter. Through military alliance treaties, the United States was able to deploy these missiles in countries neighboring the Soviet Union, placing Soviet territories under the constant threat of nuclear weapons, severely impacting national security. This threat further strained the already tense relationship between the United States and the Soviet Union. Without the Soviet V-2 rocket technology, the world, at that time, stood on the brink of nuclear disaster. But what had happened to Japan? However, engineer Lenso Serge-Kolev realized that the V-2 technology was nothing but outdated. He personally developed an entirely new technology called the R-7 missile. As soon as this technology went into production, Sputnik 1 was launched into Earth's orbit, opening the era of human space exploration and putting an end to all hopes for the US missile race. With the successful launch of Sputnik 1, the arms race gradually transformed into a space race. The United States and the Soviet Union constantly sought to surpass each other in scientific and technical achievements, partly for national security and partly because neither side could allow the other to possess superior technology. For a whole decade, the US struggled to build its own space research system. From there, massive and costly projects were funded by both sides. So what happens when the quest for space exploration is fueled by two bloodthirsty superpowers? It could be said that something miraculous occurred. At the end of World War II, Nazi Germany had developed a miraculous weapon, one that was promised to destroy the entire Allied powers with a single strike: the V-2 rocket, short for vengeance weapon, or retaliatory weapon. V-2 was an advanced technology, a rocket capable of reaching astonishing speeds and delivering an arsenal directly into the enemy's homeland. The use of rockets to attack other countries would completely change the battlefield. From now on, air combat would no longer be about manned aircraft, but rather deadly missiles falling from the sky, making the Allies tremble in fear before Hitler's might. However, while the artist's sketch was beautiful, real life didn't follow the same lines. This miraculous weapon required enough fuel to lift off, maintain velocity, and possess self-guidance capabilities, not to mention it had to carry a warhead with devastating power. The first prototype took a year to research and develop, and just 1 minute to self-destruct. While Nazi Germany was struggling to improve the situation, a young mind joined the military and elevated the research to a new level, quite literally. His name was Wernher von Braun, a young engineer in his 20s with a formidable intellect. By 1941, the pace of Nazi Germany's missile program had accelerated. The first successful missile attack had been achieved. From the primitive A-1 rocket in 1933 to the A-3 and then the A-4, the rockets had well-defined a path and produced some truly remarkable test results. In the context of Nazi Germany gradually losing on all fronts, Hitler realized he needed to bring his secret weapon to the battlefield. Thus, the V-2 rocket, an upgraded version of the A-4, was mass-produced in early 1943. The first attack by the V-2 missile sent shivers down the spines of the Allied forces. These rockets possessed immense destructive power, leveling buildings and claiming the lives of hundreds. With supersonic speed, they would hit the ground and obliterate everything before anyone could even hear them coming through the sky. The V-2 attacks weren't just about causing physical damage, they were psychological warfare aimed at the innocent public. In the minds of civilians, they could vanish at any moment without warning. It was truly a nightmare where no place and no time could be considered safe. However, as dangerous as these attacks were, the V-2 missile ultimately proved to be a strategic misstep for Nazi Germany. Allied spies quickly caught wind of the rocket program and managed to steal several units during transport. Thanks to that, Allied forces were able to understand how the rockets worked and pinpoint their production sites. Raids on the missile factories plunged Nazi Germany into deeper disaster. The V-2 did not serve any specific military strategy. Instead, it caused random casualties. Some rockets failed, some hit their targets, but most were shot down by military aircraft. Moreover, mass production began right around the catastrophic defeat at Stalingrad, making these sensitive weapons not only expensive, but also a financial burden on the Nazi regime. It left Hitler tearing his hair out, desperately trying to turn the tide. During wartime, every move needs to be calculated carefully. With the V-2, Nazi Germany drained its finances for a weapon that was not particularly effective, easy to intercept, and ultimately nothing more than a thorn in Hitler's side every time he sat down. What's more, once the Allies had their hands on the Nazis' technology, they immediately studied it and found ways to turn it into a weapon for their own use. And from here we begin to understand why the fascists collapsed so quickly. After World War II ended, the looming threat of a V-2 missile race sent both the United States and the Soviet Union scrambling to find the mastermind behind the weapon. As soon as the guns fell silent, Werner von Braun was captured by the Americans and brought to a facility to serve a new purpose, designing rockets for the United States. Thus began a new era. While the Americans terrified the world with the 2 bombs they dropped on Japan, Lenzo had quietly moved ahead. The Americans had acquired Werner von Braun, but the Soviets had their own geniuses, and they continued developing their technology. Just a year after working for the Americans, von Braun created a new rocket called the T-Viking, with several upgrades in engine performance and control capabilities. After that, the US continued to improve upon wartime products and eventually developed a new type of rocket, the Enlov missile. On November 24, 1947, the first public test of the A-1RB rocket was carried out. However, the rocket encountered a malfunction and flew to the wrong location. This issue was fixed in the following test. Then came the RB-3, which broke the sound barrier in an instant and became the most successful test up to that point. The development of the AOB rocket series continued to accelerate, and it achieved significant milestones when the rocket managed to reach outer space, far beyond the Earth's protective atmosphere, an achievement made possible thanks to the father of the V-2 rocket. The United States quickly gained dominance of the skies. Although the Soviet Union did not have von Braun, they had managed to acquire a large number of V-2 rockets for their own research and development. In 1947, Soviet scientists successfully reverse-engineered and launched their own version of the V-2 rocket. Just 1 year later, they had upgraded the V-2 into a more complete version called the R-1. In the years that followed, the Soviet Union continued to develop new rocket models based on German technology. However, by the time the R-5 was created, Soviet engineers realized that the design was already outdated. From 1954 to 1957, engineer Sergei Korolev and his colleagues began refining rocket technology, abandoning the weak design of the V-2 in favor of their own innovations. Eventually, they developed the first intercontinental ballistic missile in 1957, known as the R-7. In August 1957, the R-7 test launch was conducted, with results exceeding expectations. The R-7 became the most powerful rocket in terms of thrust at the time of its debut. From then on, the Soviet government realized it was time to push this technology forward and turn it into a scientific monument, officially positioning the Soviet Union as the victor in the technology race during the Cold War era. Their goal now lay beyond the atmosphere. They wanted to send humans into space, but this was also the moment when things became more serious. Unlike the Nazi V-2 rocket strikes, the refined rockets of the United States and the Soviet Union were born after America had already demonstrated to the world the raw power of technology. Oppenheimer and his colleagues had harnessed the energy of the stars to vaporize 2 cities in Japan. Now both of the world's superpowers not only held massive nuclear arsenals, but also possessed the technology to launch those warheads into the sky. What would happen next? The United States, being the first to possess nuclear bombs, found that developing and owning ballistic missiles was essentially like pointing a gun at the entire world and declaring that they could shoot anyone, anywhere. On the other side, the Soviet Union fully understood the danger of such weapons falling into enemy hands, and thus they were compelled to accelerate their own nuclear weapons development. The Soviet government's effort to design nuclear bombs didn't start only after the Americans had theirs. Even during the war, spies had already reported back to Stalin about what was happening in Los Alamos, about the discussions between Oppenheimer and his colleagues. Therefore, since the 1940s, the Soviet Union had already begun developing its own atomic bomb. However, the process of building the bomb was slow due to numerous issues related to limited manpower and funding. The Soviet Union could not keep up with the United States in this race. Nevertheless, after witnessing the destructive power of the bombs dropped on 2 cities near its own borders, the Soviet Union reconsidered and began investing all its resources into the development of nuclear weapons. Eventually, the first Soviet atomic bomb was successfully detonated on October 25, 1946. In the following decade, the missile race between the 2 superpowers threatened global security to a suffocating degree. Both sides had nuclear bombs, both had ballistic missiles. So what was stopping them from producing a third installment of the World War series, this time titled Nuclear War? The short answer, nothing. The Soviet Union continued to push forward its nuclear program alongside its missile program. By 1955, they had developed a bomb even more powerful than Oppenheimer's atomic bomb, a hydrogen bomb, 100 times stronger. They had already tested atomic bombs 6 years earlier. The missile race was no longer just a competition to see who would reach space first. Instead, it had become an issue of national security, and on a broader scale, global security. The one who dominated the skies was the one with the power to press the red button and wipe the other nation off the map. Therefore, after possessing both atomic and hydrogen bombs, the remaining question became, who would be the first to reach space? And who would be the first to bring nuclear weapons into space? In that race, the Soviet Union took the lead with Sputnik 1 in 1957. The existence of a satellite in the sky shook the United States' standing as the nation with the most advantageous geographical and strategic position. In response to the public uproar, the US pushed forward once again and unveiled its trump card, the Vanguard rocket. Vanguard was a project funded by the US government intended not only to match Sputnik, but also to reassure the public, who now lived under the looming shadow of death above their heads. Nevertheless, due to the rushed development process, Vanguard became a laughingstock when it managed to fly for only 2 seconds before exploding, leaving the entire American public in shock. That failure was quickly broadcasted by the Soviet Union on every newspaper, mocking and ridiculing the efforts of the nation once known as the first to possess nuclear weapons. While the United States still had no official response to Sputnik, the Soviet Union delivered yet another blow by sending the dog Laika into space aboard Sputnik 2 at the end of 1957. In an effort to close the gap with the Soviet Union, the US government successfully launched the spacecraft Explorer 1 into space in 1958. Around this time, President Eisenhower established the National Aeronautics and Space Administration, NASA, to directly oversee the development of space technology. However, the successful launch of Explorer 1 meant little in the space race, because while the United States had just managed to send its first satellite, the Soviet Union already had new plans. In 1961, Yuri Gagarin became the first human in space, marking the most significant milestone in the entire race. In response to the Soviet Union's challenge, the United States sent Alan Shepard into space just 3 weeks later, and John Glenn into Earth's orbit in 1962, making the race incredibly tight and breathless. Eventually, it seemed the United States had grown weary of constantly chasing the Soviet Union, of trailing behind the rocket smoke of Red Army comrades. So they turned their eyes to the successor of President Eisenhower and waited for his answer. At the end of 1962, John F. Kennedy, the 35th President of the United States, stood before the American people and declared that he would put Americans on the moon. When elected, John F. Kennedy faced immense pressure as the United States was continuously being outpaced in the technology race. Throughout his term, the president consistently pushed for increased investment in space research projects, believing that only by doing so could the US surpass its rival in this competition. To achieve the set goal, a series of major projects were launched from 1966 to 1969. In 1966 alone, the US initiated 3 projects, Apollo 1A, 2, and 3. Scientists tested numerous materials for spacecraft construction and calculated the amount of fuel needed to reach the moon. After thorough preparations, at the beginning of 1967, the succeeding president, Nixon, authorized a test launch of the Apollo 1 spacecraft, designed to carry 3 astronauts to the moon. However, as the first crewed spacecraft model, it encountered problems during takeoff and quickly caught fire. What happened afterward plunged the entire world into silence. The 3 astronauts, G. Grayson, Ed White, and Roger B. Chaffee, were tragically burned alive inside the cabin. Facing this disaster, the authorities had no choice but to continue moving forward. From Apollo 4 through Apollo 6, scientists continuously improved the spacecraft's hull materials and propulsion power. However, to avoid further accidents, these test missions no longer carried humans on board. It was not until Apollo 7 that astronauts were allowed on the test flight in preparation for the official mission. This positive progress restored hope among researchers and the American public alike. In 1968, American astronauts were able to reach orbit and travel a considerable distance over a 20-hour period. Meanwhile, life support systems were nearly perfected, and the path to the moon was no longer so distant. The sudden death of Kennedy and the subsequent political turmoil did not significantly affect the Apollo project. The then current president, Nixon, continued to nurture Kennedy's unfinished vision and invested further in the program. As a result, in 1969, astronauts successfully carried out Apollo 10, the final step before humanity's first moon landing. Then, at the end of 1969, Neil Armstrong, Michael Collins, and Edwin Buzz Aldrin boarded Apollo 11, preparing for the most important journey not only of their lives, but of all mankind. And on July 20th of that year, Neil spoke into his radio the words that humanity would remember forever. With the setting foot on the moon, the space race officially came to an end. Thanks to John Kennedy's challenge, the United States overcame all difficulties and reached out to the infinite, touching a place that we had only dared to dream of before. Now, the technology race was no longer about armament. What had happened, but space was no longer a prized possession for profiteers to claim. At least, the relationship between the United States and the Soviet Union had changed in a positive direction. In 1971, the US and the USSR held a historic meeting, creating what could be considered the most moving project of the entire Cold War, the Apollo-Soyuz project. This was the moment when both nations brought their manned satellites together and created something history had never imagined, a celebration in space. On December 6, 1971, engineers from both countries met, exchanged information, and shared the design of the space docking module. Thanks to this, the docking modules of the two satellites could connect and create a door for the two crews to meet in the vastness of space. And on July 17, 1975, a warm handshake ended the Cold War between the two superpowers. The first rocket launch had ignited the technology race between the two powers, the United States and the Soviet Union. This was an extremely fierce covert war, as both strong nations threatened each other with the most advanced weapons they could create. However, when President JFK announced he would send Americans to the moon, a new chapter of the race was drawn. How did they get to the moon? What did they have to do to reach the moon? And what would happen when we touched the surface of the satellite? The Cold War was not always a balanced contest. Throughout the technology race, the United States continuously found itself in the shadow of Soviet rockets. First came the Vanguard incident, a blemish on American technology, and then the Soviet Union succeeded in putting Sputnik into orbit around the planet. All of these events revealed the weaknesses of the United States before the Red Army comrades. Perhaps it was when Yuri Gagarin stepped into space that the US government ran out of patience and realized a bolder step was needed to escape the shadow of the Soviet Union. Therefore, after NASA was established, President JFK announced to the world that he would send humans to the moon. However, as the late president himself said, this was not a simple task. Before talking about sending humans to the moon, we must first understand the mechanism of getting humans into space. The first question to ask is, how do you fly out there? The invention of the aeroplane changed the world. Since humans could rise above the clouds, we dreamed of breaking through the planet's atmosphere and reaching the stars. But that dream was still quite distant. The reason we remain standing on the ground instead of being flung off the planet is due to a special interaction called gravity. Gravity results from the interaction between mass and space-time. The greater the mass, the stronger the gravity, and with Earth's mass, its gravity acts as a pulling force directed toward the planet's core. Thanks to gravity, everything on this planet is falling toward its center at a speed of up to 9.8 meters per second squared, and this is the biggest problem in sending humans to the moon. Exceeding escape velocity is not exactly difficult. We can achieve this with advanced engines. However, maintaining a vertical speed sufficient to break free from the planet's influence is extremely hard. To generate enough force to escape this planet's gravity, a rocket must carry enough fuel. However, carrying too much fuel makes the rocket heavy and thus requires even more fuel to produce enough thrust to carry that additional weight. But because of the added weight, more fuel is again needed. This loop of balancing mass and fuel continues endlessly. This is the foundation of rocket technology, which mainly revolves around optimizing fuel usage. With modern technological advances, this is no longer too difficult for scientists. However, in the post-World War II era, when rockets were just invented, Optimizing fuel was like trying to build a bridge while crossing it as fast as possible. Because of this context, scientists faced countless challenges in building the spacecraft: how to ensure it could move out of Earth's atmosphere with a reasonable amount of fuel, how to make it withstand the heat generated by air friction, how to accelerate in space after escaping Earth, and so on. Despite these enormous challenges, the good news was that rocket scientists had many prior projects to use as data sources and to continue developing. Thanks to data from previous projects, the first design of a moon rocket was created, called the Nova spacecraft. Nova was not actually a single spacecraft, but rather a new category of rockets intended for lunar missions. However, the initial design for the Nova rocket and spacecraft was truly bulky and definitely exceeded the available budget for development, so it was quickly discarded. After the Nova design, NASA engineers developed a new rocket launch system consisting of 3 stages. Each rocket engine served a specific purpose during the journey to the moon. The first engine was used to launch the entire system into the sky, and was then detached to reduce weight. With less mass, the second engine could accelerate the rocket to achieve orbital altitude, and after this second engine was jettisoned, the third engine would propel the spacecraft toward the moon. This ingenious design not only allowed the rocket to be lighter and fly farther with a more cost-economical budget, but it was also easier to build since its multiple components could be constructed simultaneously and then assembled into a large rocket. Thanks to this clever design, this rocket went into production to serve the moon mission. The Saturn rocket was designed with 3 parts, with the first stage being the largest. This part contained the rocket fuel and liquid oxygen necessary for combustion. Beneath the 2 fuel tanks were 5 F-1 engines manufactured by Boeing, responsible for burning all the fuel in the engines to lift 3,000 tons into the sky. Each engine could produce 620 tons of thrust. Not only enough to lift the entire rocket, but also to accelerate it to speeds exceeding 8,000 km/h. 5 months after JFK's speech, the first Saturn rocket was completed and ready for test flight. That successful launch marked the beginning of a series of test flights for the Saturn I rocket to calculate optimal fuel use and a suitable flight path for the mission. Thus, Saturn I, then Saturn II, and finally the most optimized design, the Saturn V rocket, were completed for the mission to send humans to the moon. From here, the remaining task was to build a cockpit capable of carrying astronauts, transporting them to the moon, and maintaining effective communication with Earth. So, how did everything unfold? The Saturn rocket's mission was to send humans to the moon, but the vehicle that actually allowed the astronauts to set foot on this natural satellite was a small spacecraft housed inside the rocket. The rocket's job was simply to lift it into the sky. This spacecraft was called Apollo. It was also the name tied to both NASA's greatest triumphs and its tragic failures. While the rocket was nearing completion, the Apollo 1 cockpit was gradually finished and put into testing. This was the time for astronauts to sit in the cockpit, familiarize themselves with the controls, and rehearse the mission, practicing the procedures they would use while in space. The people involved in the process included Gus Grissom, Ed White, and Roger Chaffee, the first crew to test the initial Apollo spacecraft. They were suited up in spacesuits to familiarize themselves with the gear. Afterwards, they were placed inside the test cockpit, which was set in a simulated vacuum environment to help them acclimate, and then began the subsequent procedures. During the entire process, some malfunctions occurred, such as communication signal issues, which caused the test to be delayed. The nearly 2-hour delay tested the astronauts' patience. Gus Grissom actually wondered how they could possibly get to the moon when even communication on the ground was not working properly. And he was right. They never made it to the moon. After hours of delay, an electrical accident occurred inside the cockpit, leading to a massive fire in the confined space. The fire, fueled by the pressurized atmosphere, turned into an explosion within the sealed cockpit. The cockpit, designed to protect the astronauts in space, became their tomb, as it also prevented them from escaping in time. All 3 astronauts were burned alive in an instant, and the entire Apollo program had to be halted. Following that horrifying event, NASA banned the use of astronauts in cockpit tests until safer conditions could be ensured. Therefore, the Apollo cockpit tests from 2 to 6 were conducted without direct human involvement. The Apollo 4, 5, and 6 missions were organized to monitor the situation after the Apollo 1 incident, and the result was the successful launch of Apollo 7, which returned astronauts safely to Earth orbit. This flight was extremely important as it contributed to a critical phase of the mission, the orbital docking station, around Earth. Next came the Apollo 8 and 9 flights to test the equipment that would be used on the Moon and to recheck the feasibility of the spacecraft's trajectory. Apollo 10 had all the equipment and rocket systems ready. NASA sent astronauts on a full orbit around the Moon and back to Earth. This trip is considered one of the greatest successes because it marked a key milestone on the path to the Moon, confirming that the mission was entirely feasible and that preparations for the next trip, Apollo 11, could proceed. This was a journey that future generations would surely recount many times. But how exactly did they get to the Moon? Was it just a matter of firing a rocket, and that's it? The distance between the Moon and Earth is often misunderstood in textbooks. We always see the Earth and Moon side by side, as if they were very close to us. We also know that tides are caused by the Moon's effect on the Earth. So naturally, this natural satellite must be extremely close to us, right? This is a thought that, while quite accurate, is actually very misleading. Of course, among all the celestial bodies in the solar system, the Moon is the closest to us, but closest is not as near as we tend to imagine. The distance between the Moon and the Earth is 384,400 kilometers, a staggering number. To understand just how vast this distance is, we can imagine fitting all the remaining planets in the solar system between the Earth and the Moon, and still having about 8,000 kilometers left over to put something else in. That distance can hold not only the 3 rocky planets of the solar system, but also the 4 giant gas planets, including Saturn, which is almost as large as a fraction of the Sun. In short, this is an incredibly huge distance. So how do we get to such a faraway place? Besides getting the spacecraft off the planet, we also have to figure out how to travel the enormous distance between the 2 celestial bodies. Fortunately, basic physics will take care of that for us. Everything in the universe follows the laws of motion discovered by Newton. As he stated, an object moving in a vacuum will maintain its velocity unless acted upon by an external force. This means that once a spacecraft reaches the vacuum of space, the velocity it gains after launch will be maintained without needing extra fuel to reach the Moon. The only thing we need to do is wait. That sounds interesting, but how exactly do we get to the Moon? After all, the Earth is spinning, right? If we launch a rocket without careful aiming, could it possibly crash straight into the Sun? This is where the concept of a stopover in Earth's orbit becomes truly important. Everything on Earth is affected by the gravity it produces. If we throw a paper aeroplane into the air, it will definitely fall back down. But if we give it enough force to fly very high and very far, it will still fall, but its landing point will be outside the planet. Therefore, it will become an artificial satellite that keeps orbiting the Earth without falling down. This is because its landing point is exactly on the orbit it is flying. This is what we call Earth's orbit, a place where satellites can safely rest without worrying about falling. When the Saturn V rocket is launched into orbit, both the Apollo spacecraft and the astronauts can take a temporary rest there, waiting for the signal that they have reached the perfect zone to launch and fly straight to the moon. When that signal comes, all they have to do is press a button. Then the final rocket will ignite and send the entire crew to the moon. Truly, this is a path filled with ingenuity and genius. However, reaching this point is not the end of the story. Sending humans to the moon cannot rely solely on rockets, spacecraft, and orbits. It also requires ways to protect the astronauts from the deadly dangers of outer space. During the Cold War, the technological race sent many space explorers high into the sky and tested various materials to protect them. But exactly what do scientists need to shield the astronauts from the first challenge astronauts face is the harsh conditions of microgravity. The concept of the vacuum of space is something we do not experience standing on the Earth's surface. When exposed to a vacuum, a strange phenomenon occurs. First, because there is no atmosphere, the air inside an astronaut's lungs will diffuse and try to escape. Without a sealed protective suit, the astronaut would certainly die. Next, also due to diffusion, the water molecules in the body will try to escape and dissolve into the vacuum. This causes the water on the surface of their skin to boil instantly, especially in the mouth and eyes. Moreover, Earth's atmosphere protects us from the deadly radiation of the sun. That means once we leave our natural shield, we will be burned by the radiation from the nearest star, the sun. This is not just a severe sunburn, but affects the body at the cellular level, greatly increasing astronauts' risk of cancer compared to normal people. With a sealed and somewhat restrictive suit, it acts like an oven and requires a cooling system for the astronauts' bodies. To achieve this, engineers have created a water cooling system that circulates throughout the body to help the crew breathe easier. Beyond radiation and the harsh vacuum conditions, astronauts also face space dust, particles flying at terrifying speeds. Because nothing in space slows them down, these dust particles have immense destructive power if they collide with the astronauts' bodies. Therefore, astronaut suits must be airtight, radiation-resistant, and sturdy enough to withstand these space bullets. To accomplish this, the suits are made of 11 layers of different fabrics, including layers that insulate, resist moisture, repel water, protect against heat, abrasion, and fire, and the outermost layer is bulletproof. Finally, the suit needs a special helmet that contains all these properties along with other features to ensure a safe working environment for the astronauts. Space is a place where sunlight shines without clouds or the ozone layer to protect. Therefore, astronauts need a special visor to avoid direct sunlight. The first layer is transparent so they can see everything around them. The second layer is woven with gold to block solar radiation, including heat and intense light. The final layer of the helmet is a hard metal shield to block all light used when facing the sun directly. This mode is necessary because space has no concept of day and night. The brightness astronauts experience depends on their position relative to the sun. If they travel through the vacuum, they constantly face sunlight, while if they stand behind the Earth or the Moon, they receive no light at all. Therefore, the helmet must also have a built-in flashlight to ensure they have enough light to work. Finally, the astronaut suit needs a place to contain and operate all these features, which is the large backpack on their back. This is where the oxygen tanks are stored, large enough to provide breathable air for up to 7 continuous hours. In addition, it must have a CO2 filtration system to prevent suffocation, as well as a cooling system, batteries to power the suit, and a communication system to connect to the radio. At this point, the suit is quite advanced, but to operate it there is also a control panel located on the astronaut's chest. The control panel allows them to press the radio call button, regulate humidity and water circulating in the suit, and manage several other special functions. Depending on the mission, and so the astronauts can see the buttons on the chest panel, there is even a small mirror attached to their arm to help them look at their chest. The main reason is that they cannot bend down to see, and to view the information clearly through the mirror, the buttons and information on the chest are written in reverse, so they can understand it via the reflection. That is not all. Astronauts cannot live forever inside that protective shell. From the moment they leave Earth until they land on the Moon, they need breathable space and a normal living environment inside the spacecraft. Therefore, the spacecraft itself must be able to withstand vacuum conditions. Inside the spacecraft, it must not only be airtight, but also have an airlock to maintain stable air conditions. Additionally, it needs an outer shell that is bulletproof, fireproof, abrasion-resistant, waterproof, and resistant to many other hazards. Structurally, the spacecraft must have a cockpit with full amenities, controls to pilot the ship, and communication equipment to report back to Earth what is happening. There must also be a living area for astronauts to sleep, eat, and of course a restroom. In a zero-gravity environment, our bodies do not function as they do on Earth. First, it is unclear whether we feel hungry or need to use the restroom because food, drinks, and even urine in the bladder do not flow downward but float inside the body. For this reason, our bodies do not send clear signals to indicate hunger or the need to relieve ourselves. Therefore, astronauts must follow a very strict regimen for eating and sleeping to maintain their health. Their food and drinks must also be specially packaged for the vacuum environment. We cannot place food on a table because everything would float away. Instead, all food and drinks come in sealed tubes, like toothpaste, in each meal. Astronauts squeeze the contents directly into their mouths and swallow. How did scientists come up with these solutions to design the suits for space travel? In fact, this was a massive research project spanning from the time of World War II to the beginning of the Cold War space race. Advanced diving and naval suits were adapted for the space environment because they shared the same purpose, protecting the wearer in harsh conditions. The first contributors to this work included Jeff Kenney, who created a high-pressure suit in 1931 for the Soviet Red Army. Next was Emilio Herrera, who developed high-pressure suits for supersonic flight missions in 1935 and 1936. Finally, and most notably, Ross Colley designed the official astronaut suit for the Mercury project, which took Alan Shepard into space in May 1961. As for the spacecraft carrying astronauts into space, its creation was the result of the collective efforts of researchers and engineers working at NASA and affiliated companies like General Dynamics, Lockheed, and North American Rockwell. At this point, everything was ready, from the rockets to the flight paths, to the suits and the spacecraft. The only remaining factor was the crew. The crew member was a top student named Bain, who was allowed to choose where to train and selected the US Air Force. By 1947, from a student, he became a lieutenant and trained in the Air Force in Florida, gaining many years of flying experience in Germany, Korea, and a slew of special achievements. Bain was selected for the Apollo program and quickly became a member of the astronaut team for Apollo 11 in 1962. Michael Collins was the next to join the ranks. He also had an impressive flying record with 3,000 hours, of which 2,700 hours were on jet aircraft. The last, and no less important, was Neil Armstrong, a Navy pilot, test pilot, and aerospace engineer. The three boarded the Apollo 11 spacecraft and were launched into space on July 16, 1969, to the amazement of all eyes on Earth. The rocket, designated S5AS6, propelled Apollo 11 skyward. After 2 minutes, the rocket entered its next stage and jettisoned the initial booster. The second engine ignited and began its burn, separating after about 9 minutes to prepare for the final stage. When Apollo 11 entered Earth's orbit at about 185 km altitude, specifically after 12 minutes, the second engine was discarded and the third engine ignited, propelling the crew directly toward the Moon, the natural satellite of our blue planet. Back on Earth, the celebration of the successful launch was quickly set aside to focus on the crew's next journey. The landing on the Moon took place on July 20. The spacecraft reached lunar orbit. Bain and Armstrong entered the Eagle module to prepare for landing at 1744. The Eagle separated from Columbia and descended to the Moon. Meanwhile, Collins remained aboard Columbia to ensure Eagle's successful landing. After a tense moment, Armstrong radioed back to Earth. "The Eagle has landed." What happened next is known to everyone worldwide. The first words spoken by the man who set foot on the Moon were broadcast over the radio, elevating humanity to a new level in the quest to conquer the vast universe. Both on the ground and in the air, cheers erupted in celebration. After so much suffering, sacrifice, and loss, both of lives and resources, the seemingly impossible mission had finally been accomplished. The whole world was astonished and overwhelmed with indescribable joy, unable to understand exactly why they felt so proud of people they had never even met. All anyone knew was that they were witnessing history, and felt immense pride in that fact. However, the mission was not yet over. To send humans to the Moon, we had to invent rocket science and face countless challenges, with numerous rocket tests, both successes and failures, before achieving this historic journey. But one thing we had never done before was to launch from the Moon back to Earth. Bringing humans to the Moon was an enormous challenge for scientists, engineers, and rocket science researchers, a field that had only been developed relatively recently. The research and development to create tools capable of sending humans into space had only truly been underway for a few years, so the existence of the Saturn V rocket was already a miracle of science and engineering. Yet on the Moon, there was no Saturn V to launch the astronauts back to Earth. Fortunately, we did not need a giant rocket to return humans to our home planet. Earth's gravitational acceleration is approximately 9.8 m/s2, meaning Earth pulls us back at that rate. Meanwhile, the Moon's gravity is much weaker, only about 1.62 m/s2, so instead of needing a massive rocket to push us back into space, we only required just enough thrust combined with a relatively small launch force. The greatest challenge was probably not jumping off the Moon, but figuring out how to get back to Earth. This is where Eagle and Columbia come into the picture. After sending the crew beyond Earth's reach, the Saturn V rocket discarded 2 of its stages and left only the third stage, which included the third engine and the main crew module. Once in the vacuum of space, the third engine had completed its task. The entire spacecraft had reached the velocity needed to reach the Moon, and in the vacuum there was no friction to slow it down. According to Newton's first law of motion, an object in motion stays in motion with the same velocity unless acted upon by an external force. So this was the time to discard the third engine and prepare for the next step. This stage not only involved discarding the third engine, but also some special maneuvers. First, the astronauts moved to the capsule at the tip of the rocket, detached it from the rocket, and inverted it. After flipping the capsule at the tip, they connected it to the main crew module and pulled it away from the third engine. Why was this necessary? The capsule at the tip of the rocket was called Columbia, and the capsule they pulled away from the third engine was called Eagle. Upon reaching lunar orbit, Columbia would push Eagle away so that Eagle could land on the Moon, while Columbia remained orbiting the satellite. While Eagle carried out its mission on the lunar surface, Columbia stayed floating above, held in orbit by the Moon's gravity. When Eagle had completed its mission, we come to perhaps the most important part of the entire journey. First, Neil Armstrong and Buzz Aldrin would return to Eagle and prepare for liftoff. Their trajectory had already been predetermined, and Eagle would use its legs to push off the lunar surface, allowing them to hover above the ground. Because the Moon's gravity is much weaker than Earth's, this thrust would be enough for them to lift off. The rest of the work would be done by the small rockets beneath Eagle. These rockets had initially helped Eagle create the thrust to land on the Moon, and now they were responsible for accelerating Eagle back into space to rendezvous with Columbia in lunar orbit. Now reunited, Armstrong and Aldrin transferred to Columbia and joined Michael Collins. The three of them left Eagle behind after moving all equipment and samples aboard. After traveling halfway around the Moon's orbit, Columbia ignited its rocket and launched back toward Earth. But even then, the mission was not over. Returning to Earth could not be as simple as flying straight into the planet, as that would have been akin to a catastrophic crash. Therefore, a landing plan was devised even before the mission was fully conceptualized. When nearing Earth's orbit, Columbia would separate once again. While the entire spacecraft flipped upside down, the discarded engine would fall back to Earth, and the crew module would remain in space during this maneuver. This flipping of the crew module was critically important because it allowed the large surface area rather than the pointed nose to face Earth's atmosphere. This larger surface, the bottom of the spacecraft, was covered with a very thick heat shield to prevent the astronauts from burning up during re-entry. When the capsule reached a suitable altitude, parachutes would deploy, allowing a safe, controlled descent into the ocean. Upon splashdown, the spacecraft would send out a signal to nearby Navy ships to locate and retrieve the astronauts and bring them home. At this point, the mission was officially complete. Why did they do all this? Looking at the journey to the Moon and back, one cannot help but wonder what motivated these people to achieve such extraordinary feats. It all began with the space race, fueled by fear. Fear of who would possess weapons of mass destruction first, who would develop ballistic missiles first, and then the race shifted to who would dominate the skies. Countless rocket tests consumed endless paperwork, effort, and time from countless unknown individuals, followed by the tragic Apollo 1 test and the heartbreaking death of 3 young astronauts. Yet despite a future full of challenges and uncertainties, they continued onward. They knew that out there lay the vast, infinite universe, a place humanity did not understand, and perhaps would never fully understand. Death was only inches away from them. Just one loose seal, one misplaced speck of cosmic dust, or a single malfunction in their suits could have meant certain death during the landing on the Moon. Even moving around on the lunar surface was no small challenge. We were born on Earth, and evolution gave us legs made for walking on this planet, not on the Moon. Yet they still went. Challenges piled upon challenges throughout the decade, all culminating in a mission lasting less than a week, as if shouting in Armstrong's and his teammates' faces to not go, to do nothing at all. But they went anyway. Let that sink in. If you were Armstrong, Aldrin, or Collins, you had 2 choices before you: to board the Apollo and face death every second, or stay home and embrace an open future? What would you choose? More than 50 years have passed since Neil Armstrong and his comrades took humanity's first steps on the moon, marking a monumental milestone in human history. It was the day the historic race between the Soviet Union and the United States ended, the day technology and human science turned a new page. Following Apollo 11's success, the US government continued to launch 6 more spacecraft. In a short time, 12 American astronauts set foot on the moon. Yet something strange happened. Since Apollo 17 in 1972, the US cancelled all subsequent Apollo missions. Why? Was there something preventing them from returning to the moon? Or was the US government hiding something to achieve the goal President Kennedy once set? The government had invested an enormous amount of money. At that time, the cost of these projects exceeded $20 million. However, it was never finances that deterred humans from returning, but the moon itself, a place utterly deadly. Throughout its history, the moon has been constantly bombarded by meteorites, pulverizing its rocks. Moreover, its surface is continuously weathered by solar wind, making the dust increasingly fine. On top of that, the moon is a celestial body without an atmosphere, meaning it has no ecosystem to clean its surface. For this reason, after billions of years, it has become an incredibly dirty, dusty place. Essentially, the moon is a mass of soil without an atmosphere, so its surface constantly endures solar radiation. Because of this, lunar dust particles are magnetic. The magnetic field in the moon's dust is so strong that these particles can lift into the air and then fall back down. This phenomenon is called the lunar fountain. It is named so because when exposed to the sun's ultraviolet rays, the dust particles are repelled by the radiation's magnetism, rising into the sky and then slowly falling back down like a fountain. Moreover, lunar dust easily clings to spacesuits and can enter astronauts' bodies due to its strong magnetism. Therefore, lunar dust is not only highly adhesive, but also prone to causing malfunctions in the spacecraft's electronic components. Moreover, lunar dust has a very high abrasive capacity, so spacesuits often develop many holes after being used for some time. When dust-covered suits are exposed to sunlight, they absorb heat much faster than usual. This makes lunar exploration increasingly difficult for astronauts. Given how dangerous lunar dust is, what would happen if it entered the human body? When humans first landed on the moon, we did not anticipate the destructive power of this environment. After only 2 hours on the lunar surface, the Apollo 11 spacesuits were completely unusable. Later, when scientists received and studied this dust, they were amazed by what they discovered. Lunar dust is formed from alloys and glass. It is composed of solid materials, yet the dust itself is incredibly fine, almost like powder. To determine the composition of this dust, scientists had to use microscopes to examine the smallest particles. Even worse, these dust particles are highly magnetic, so they cling strongly to spacesuits after use. As a result, when astronauts return to the spacecraft, they bring a large amount of dust inside. These particles then stick to the ventilation tubes inside the ship, which the astronauts inhale. This is when the real horror of the moon begins. To understand what happens when this dust is inhaled, a group of students at Stony Brook conducted an experiment by introducing lunar dust into artificial lung fluid. After about 15 minutes, they observed hydrogen gas released from the solution. Additionally, the reaction produced substances that gradually weakened the body over time. Normally, when we enter dusty environments, our bodies respond by sneezing to prevent dust from entering deeper. However, lunar dust is a different story. The body still reacts by sneezing, but the lunar dust sticks to the respiratory tract, lungs, and brain. Therefore, the impact of this dust causes far more than just lung damage. It tears apart cells in both the lungs and brain. This triggers a chain reaction inside the body that eventually leads to cancer and lung diseases. Furthermore, when lunar dust comes into contact with human skin, it causes redness and itching. At first, astronauts were unaware that lunar dust was made of glass particles. Consequently, when itching occurred, astronauts scratched the irritated skin, worsening the damage. Then, of course, once lunar dust comes into contact with the skin, damage to the eyes is only a matter of time. When lunar dust gets into the eyes, it scratches the cornea and gradually leads to blindness. After 6 Apollo missions, American scientists improved the durability of the spacesuits from 2 hours to up to 20 hours. However, even that was not enough. Under the influence of lunar dust, support equipment still remains a difficult problem that has yet to be solved. Furthermore, scientists have not yet found a way to clean the suits so that lunar dust does not stick to them. When trapped in the joints, the dust destroys all machinery, causing everything to stop working, and it is especially harmful to the health of all astronauts who repeatedly travel to the moon. Therefore, after considering all these issues, following the final Apollo mission, the US government decided to suspend the project until they could find a way to deal with this dust. From 1968 to 1972, the US government successfully launched 6 out of 9 Apollo missions to bring humans to the moon. However, due to the technological limitations of the time, we were unable to solve the difficult problem mentioned above, which is lunar dust. As a result, scientists worldwide joined forces once again to try to bring humans back to this satellite. The project named Artemis embodies decades of global effort, making it an extremely significant mission. The Artemis project is not only about landing on the moon, but also about bringing back data that will help humanity set foot on Mars in the future. So how will NASA carry out this return mission to the moon? The Artemis spacecraft focuses entirely on protecting the astronauts, starting with the most important part, the Orion Command Module. This module will be the living and working space for 4 astronauts throughout the flight. The module uses technologies to simulate Earth's environment. Additionally, it is equipped with its own engines and technologies to help astronauts easily return to Earth. The Orion module is shielded by the spacecraft's nose cone and has the ability to launch itself away to ensure crew safety in case of a launch failure. The launch system is arranged in a sequence including the cargo bay, the booster, and after detaching the main booster, 2 rockets support the journey into orbit. The main booster is designed with 4 RS-25 engines, capable of producing up to 2,000 tons of thrust. Scientists have also changed the mass distribution of each module to achieve more efficient launches. Moreover, the fuel for the Artemis Block 1B spacecraft has been adjusted, significantly improving its thrust. With these outstanding improvements, Artemis Block 1B officially becomes the most powerful spacecraft to date. Upon reaching Earth's orbit, the entire engine section of the spacecraft is detached to allow easier movement in space. Then, the auxiliary engine module is activated to take the crew to the moon. And of course, after 50 years, the landing method has also seen improvements, known as pre-staging. Thanks to the support of countries around the world, the Artemis project will also create a lunar refueling station called Gateway, which will support and expand future moon exploration efforts. Besides assisting with lunar landings, this station will also serve as a relay to connect and transmit information back to Earth. Given such a special mission, The lunar station is specially designed to easily connect with many other modules. This design allows the station to expand in the future, a future where humanity can send more people to the moon. The Gateway Station can even control its own orbit to land on the moon's surface, something Apollo missions could not achieve. Thanks to this capability, the station's landing orbit has a very unique elliptical shape. When Orion approaches the moon, the crew will dock with the Gateway Station by entering this elliptical orbit. After a successful connection, the crew members transfer to a lander to descend to the moon's surface. First, the station will separate the lander to exit the elliptical orbit, allowing the lander to enter a lower lunar orbit and gradually land on the surface. To protect the astronauts, their suits also need to be upgraded to withstand the harsh lunar environment. Therefore, scientists will design thicker suits, using electromagnetic technology to eliminate the adhesion of lunar dust. Once the mission to explore and study the moon is complete, the astronauts will return to the landing system to launch back into the elliptical orbit and reconnect with the Gateway Station. From there, the crew will return to the Orion spacecraft, detach from the station and head back to Earth. When Orion reaches Earth's orbit, the core capsule containing the 4 crew members will separate from the engines. Then, the Orion will turn its heat shield forward and begin the descent phase. At this point, the entire crew will enter Earth's atmosphere at speeds exceeding 40,000 km/h. Therefore, Orion's heat shield is designed to withstand temperatures up to 5,000 degrees Celsius. At the appropriate altitude, Orion will deploy a series of large parachutes to slow down, assisting with the splashdown into the ocean. NASA's plans and calculations together with the scientists are extremely clear and detailed, but all of it remains tentative, because anything can happen. That was the full story of how humanity conquered the moon, how it was defeated by it, and how we plan to return in the future. What do you think? Is this journey interesting? Please share your thoughts with us in the comments below. And if you enjoyed this video, don't forget to like, subscribe, and hit the notification bell so you won't miss any future videos. Additionally, you can support us directly by clicking the thanks or join button below. Thank you all for listening, and see you next time.